Okay, great. So, so what we're doing is we're looking at some tensor. This tensor has got 9 indices, and we've got a Young diagram here with 9 boxes. Is it 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, good. Okay, 9. Now, the way that we build this tensor is, first of all, we anti-symmetrize indices belonging to the same column, and then we symmetrize indices belonging to the same row. So there's 2 things you can do. You can anti-symmetrize or symmetrize, and there's 2 directions. This is the direction to symmetrize. That's the direction to anti-symmetrize. So first anti-symmetrize, then symmetrize. If you want to first symmetrize and then anti-symmetrize, that's also okay. Just pick one, do one first, and then do the other, and stick to your convention. Tensors constructed in this way will only mix with other tensors constructed in this way. So they form an irreducible representation, and they form an irreducible representation of GLN, so n by n matrices. Now, the question that we want to ask is, how many of these tensors are there? Don't you have some condition for the traces to be irreducible? Okay, sure. Let's make it unit determinant. Okay. So if you make GLN, you need to keep track of one extra quantum number. So we'll make it SLN, and then we're being honest. Good. Now, what I want to give you is, I want to give you a formula for this. So tensors that were constructed in this way don't mix with other tensors. Another way to say that is, this is a representation of SLN. And actually, every representation of SLN can be represented by a Young diagram. So this is a complete description of the SLN representations. And I want to give you a formula now for the dimension of this representation. Okay? So let's put, I'm just going to tell you what the rule is. Now, in fact, before we do that, let me just ask you one thing. Let's say I've got something with 2 indices. This I would call a matrix. Let me make it symmetric. So by this language, 2 indices, it's a matrix, it's symmetric. 2 indices, I would draw that. So that's how I would represent a symmetric matrix. And if I look at these symmetric matrices and I perform a transformation, which, so I should tell you what is my transformation. I have some matrix G, which is an element of SLN. And then what I will do is, I will take G, I, J, G, K, L, act on T, J, L, and this will be T primed J, L. So each of these indices I act on with an element of SLN to get the new guy. Good, that was another little test. Yes, IK, very good, okay. So this is the set of transformations that we're looking at. Now, if I've got a symmetric matrix, how many matrix elements are there in a symmetric matrix? Can someone tell me? This is an n by n matrix. Great. n plus 1 over 2. How about, let's put a tilde to distinguish it. If it's anti-symmetric, then we should draw that Young diagram. That's anti-symmetric. How many matrix elements would this have? n minus 1 by 2. So that you all know. Now if I say to you, what if it's symmetric and it's got 20 indices? I bet you're not easily going to tell me the answer, right? So that's what we're trying to do, get to an answer for that. So if it's real tensors, we're counting real components. If it's complex tensors, we'll be counting complex components.
Complex components,
yeah.
So you don't count the real degrees of freedom over complex?
No, I'm leaving that unspecified, yeah. Okay, good. So this is what we do. In the first Young tableau, you start off and you put an n inside the top corner. Every time you move in this direction, you add 1. So n plus 1, n plus 2, n plus 3. And every time you move down, you subtract 1. So this would be n minus 1, n minus 2, n plus 1, n minus 1. These numbers over here are called the factors. And now, for each box that you have in the Young diagram below, if you pick a box, let's pick this box over here, you could draw a line that goes out of the Young diagram to that side, and a line that goes through the bottom to that side. And now count how many boxes you pass through. 1, 2, 3, 4, 5, 6. That gets a 6. For this box over here, there I go down, there I come to the outside. So this is 1, 2, 3. Okay, guys, work out the number for this box. What is it? 5. For this box? 4. 3. Now some easy ones. 1. 1. 1. 2. Now, this orange elbow is called a hook. So these are called the hook lengths. The dimension of this representation is the product of the factors divided by the product of the hook lengths. So you just multiply all of those numbers divided by multiply all of those numbers. Okay? Let's check this case because we know the answer. Here we get an n, we come this one, n plus 1, divided by, now let's fill in the hooks. That's a 2, that's a 1. N times n plus 1 divided by 2 times 1. Let's try this one. There's an n minus 1, that's a 2, that's a 1. So this is n times n minus 1 over 2. So this is just a way to count tensors in general. Okay? And I'm going to keep using this rule, just as a very simple version of it, just one row. So now I want to look at the spin 2s conserved CFT current. And what we know about this current is it's symmetric. So you can swap its indices around. So let's call this J mu1, mu2, up to mu2s. You can swap any of the mu's, and that's a symmetry. It is traceless. So you can take the trace on any two indices. And it's 0, and it's conserved. Now this means that not all components of the current are independent. For example, if I use this equation, I can eliminate some components of the current. If I use this equation, I can eliminate some components of the current. If I use the fact that it's symmetric, I can do the same. So what I would like to know is how many actually independent degrees of freedom are there? That's what we want to count now. How many independent degrees of freedom? So let's start off. just ask, what is the number of symmetric tensors? To work out the number of symmetric 2S tensors, I draw a Young diagram. This has got a total of 2S boxes. Because there are 2S indices. It's just one long row because I'm looking at something that's totally symmetric. Each index here can take a total of 3 values. Before we started, we put an n plus 1, n plus 2, because each index could take n values. We can take 3 values, so here there's a 3, 4, and I keep going. This will be 2s plus 2, 2s plus 1. And then I need to divide by the hook lengths. So that's got a hook length of 1, that's got a hook length of 2, this has got a hook length of 2s, and this has got a hook length of 2s minus 1. And I need to take the product of the numbers at the top divided by the product of the numbers at the bottom. Everything at the top is going to cancel except for the 2s plus 1 and the 2s plus 2.
Why did you put those numbers from 3?
Okay, so what it is, this is the generalization. If you remember for the Young diagram, I started with an n plus 1, and so on. This n was the number of values that each index could take. Here, when I'm looking at my current, because this is in the CFT, mu1 can take a total of 3 values. So now n is 3. Yeah, exactly.
It's not the n of matrices.
Yes, it's yeah.
It's just a dimension that.
Exactly.
I just forgot the word dimension.
Yes. Okay. So now, if we start to cancel the numbers, the 2s plus 1 and the 2s plus 2 will not cancel. And then all of the numbers from the denominator will cancel except for the 2 and the 1. So that's the number of symmetric tensors. Now let's ask, what is the number of symmetric and traceless? Well, I can use this equation to eliminate components of the tensor. So the number of symmetric traceless will be the number of symmetric minus the number of equations over here. And what I have here is s minus 2 indices, and this tensor in those indices is symmetric and traceless. So I've got the number of components of a symmetric and traceless 2s tensor minus the number of components of a symmetric and traceless 2s minus 2 tensor. So this will be 2s plus 1, 2s plus 2 over 2 minus, that's the number of symmetric tensors, and then 2s minus 2 plus 1, 2s minus 2 plus 2 over 2. That's the number of traceless conditions. So 2s, 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 that cancels. 4s plus 2s is 6s. 6s, that's nothing. Minus 2s is 4s divided by 2 is 2s. 1 times 2 is 2, over 2 is 1, and that's 0 times 1 over 2 is 0. So we get 2s plus 1.
Is it just choosing 2 indices out of whatever is?
Yes, I guess.
Something like
Yeah, exactly. Yep. Something like that. Yep. And now, so that's how many symmetric and traceless tensors. Now we can ask, what is the number of symmetric, traceless, and conserved? And what you can see is the number of conservation equations looks like we have got a 2s minus 1 tensor that is symmetric and traceless. So we'll have 2s plus 1, that's the number of symmetric traceless tensors, minus 2s minus 1, that's the number of independent conservation laws. And that gives us 2, independent of spin. So for each spin, there are 2 independent components of the current. So 2 independent components. That completes the count, or completes the characterization of the CFT degrees of freedom. Those are the independent CFT degrees of freedom. Now let's try to calculate what are the independent degrees of freedom in the gravity description.
Sorry.
Yep.
So it means all the tensor J can be just written with 2 things.
Exactly. So you pull out 2 components, and just by using the conservation equation, traceless condition and symmetric condition, you can work out any component you like. Absolutely. Yep.
It's probably a dumb question, but so the first 2 are just pointwise, just linear algebra.
Yep.
Things, but the third condition is something that is for a field.
Yeah.
So
Absolutely.
I can understand the first 2. You just keep saying, okay, I can specify yay numbers. So 2s plus 1 independent numbers.
Good.
But the third one.
So the third one, when you solve it, so one thing you could do if you like, you could go to momentum space when this looks like an algebraic equation. Then solving it, however, you'll have to have a 1 over momentum component, and you'll have to specify the correct boundary conditions to fix the 0 mode of that and all of that. That can all be done. And the cost of this as well is that now it'll be non-local. Okay? So solving these equations is very nice and easy, and it works beautifully. Solving this equation is non-local, and you have to worry about 0 modes. The lovely thing in light cone gauge is that you can say 1 over d plus, and d plus has no 0 modes. So in light cone gauge, solving the conservation equation is no big deal at all. In other gauges, it's a little more complicated, but it can also be done. So you can really work out, for example, you can work out what's the action of the conformal group on the independent degrees of freedom. So there is a representation of the conformal group that acts on only those 2 components of the current, obtained by solving all of the conditions. Yeah. Good. But the last condition is different, and it gives you something non-local. So now let's talk about our gauge field. So the gauge field is something like this: A, M1, M2, all the way up to M2S. And to count independent degrees of freedom, the first thing that you need to do is you need to gauge fix the theory. So let me tell you what the so this field, I should tell you, is symmetric. It is traceless, and it has a gauge symmetry. Okay, so I can tell you what the form of the gauge symmetry is. AM1 up to M2S goes into AM1 up to M2S plus a derivative M1, and here you have some gauge parameter, which itself is a field, up to M2S, and you need to symmetrize in all of these indices because this guy is symmetric. And this is the higher spin gauge symmetry. So there's an independent gauge symmetry for every gauge field.
So So it's symmetric, not antisymmetric? I mean, it's not a form?
This is symmetrized, completely symmetrized. This guy is completely symmetrized. Now, what you...
Differential form, I mean, it's not the...
No, it's not a differential form, no. Now, if you take a look at how many functions you have here, you've got the same number of functions for 2s minus 1 indices. That's enough gauge freedom for you to take a plus m2 up to m2s equal to 0. And this is known as light cone gauge. It completely fixes the gauge. There's no residual gauge freedom left once you've chosen this. Now, if you recall, even from electrodynamics,
In this high spin gravity, I don't have any kind of gauge fields, I mean usual gauge fields.
you mean, oh, so you mean spin 1? Nothing.
I mean the antisymmetric guys, so go ahead.
No. So, okay, these are the gauge potentials. I think that maybe you're thinking about field strengths.
Yep. So this is the gauge potentials.
This is the gauge potentials, yep. Those are the fields that we usually integrate over in the path integral, yep. Now, after we pick light cone gauge, we're always going to have a constraint. Think about when you're doing temporal gauge quantization. You set A naught is equal to naught, so that's fine to pick that gauge. But then you have to impose the equation of motion that came from varying with respect to A naught. And that gauge constraint must be solved. Here too, there's a gauge constraint. Okay, so it's a technical analysis. I don't have time to go through it, but I'm going to tell you the result. So the result is easy to understand. So if you solve the gauge constraint, what it does, and this is again now something non-local, the solution is non-local, you'll have A minus is equal to determined. So anything with a minus polarization is completely determined, and it's determined in terms of A, let's say A1, A2, up to A2S. So these M's, if you remember, we introduced light cone coordinates for the AdS4. We had dx plus, dx minus, plus dx squared, plus dz squared over z squared. M could take the values plus, minus, x, or z. So those ran over 4 values. The pluses we have eliminated with our gauge condition. The minuses we solve for from our constraint. And we can express everything in terms of this field, A with a little index A. And now little index A can only be x or z. So after completely gauge fixing your theory, you only have the components of the gauge field with x and z polarizations. And what do you have? You have a gauge field A1, A2, up to A2S. It is symmetric and traceless. So let's count how many independent components there are over here for this thing that's symmetric and traceless. So the number of symmetric So again, we draw a Young diagram. Now it's slightly different to what we had before because each index here can only take 2 values, the x or the z. So we start off with a 2, a 3, and this is s plus 1 over, and now we have the hooks. One, 2, carrying on, s minus 1, 2s minus 1, and 2s. Oh, 2s plus 1. Good. And if we take the product of the factors divided by the product of the hooks, we land up with just 2s plus 1. Everything cancels from the denominator except the 1, that's nothing, and the 2s plus 1 remains from the top. So now, if we say, well, how many symmetric and traceless are there? It's exactly the same argument as we had before. So we've got 2s plus 1, that's the number of traceless guys, minus 2s minus 2 plus 1, that's the number of equations that you get after taking a trace, and that difference is 2. So there are 2 independent components of the gauge field. So the natural guesses, we've got 2 independent components coming from the conserved currents of the CFT. We've got 2 independent components of the gauge field. It seems natural to try to map the 2 independent components of the spin 2s current to the 2 independent components of the spin 2s gauge field. How do we do that? Can we actually do that? And we do that as follows. In fact, maybe let's put this up. Oh, good, great, good. Okay, so how do we do that? Yep.
Can I just quickly ask? So
Sure.
A1 up to A2S.
Yep.
Can I just fix whatever function I want, or are there like some boundary conditions as well I need to worry about?
So there's 2 functions that you need to specify. After you specify those 2, your conditions, gauge symmetry, the traceless symmetric condition, will determine all of the other components. So I haven't told you how to fix those 2 components yet. That's what we're going to talk about now. Okay? So for the gauge field, I want to do a slight rewriting now of the AdS4. So for the gauge field, I'm going to pick 2 components. I have to pick 2. I'm going to take A with all of these indices being x. And the other component of the gauge field that I'm going to take is A with all of the components being x except for the last one, which is a z. And those are the 2 degrees of freedom that I choose for my gauge field. And now I am going to repackage things in a way that turns out to be convenient with hindsight. I mean, we're going to introduce a new field, phi. This is going to be a function of x plus. It will be a function of x minus, x, z. So those are the AdS4 coordinates. But I'm going to introduce another coordinate, theta. So I've introduced a 5th coordinate. And I'll use that coordinate as follows. I'll take a sum from s is equal to 0 to infinity. I will have the cosine of 2s theta. Then I will have ax up to x over z. And over here there are 2s coordinates. Plus sine 2s theta, and we've got ax z over z, and again 2s indices. There are 2s indices. So now I've taken all of these gauge fields and I've packaged them into a single field. And the cost of this is that I've got this extra angle theta as a bookkeeping device. I'm not thinking that I'm in a 5-dimensional space. So I'm still going to use the metric of AdS4. This extra theta is just a bookkeeping device. Okay, it's just bookkeeping. Now I would invite you to compare this to the bilocal. So the bilocal was the form A is equal to 1 to n phi a of x plus x1 minus x1 phi a x plus x2 minus x2. And what you will notice is this is a single field that depends on 1, 2, 3, 4, 5 coordinates. This is a single field that depends on 1, 2, 3, 4, 5 coordinates. So can we identify those two fields? Is this giving us the higher spin field? And if so, how are the coordinates of the CFT to be identified with the coordinates of the higher spin gravity? So, in fact, it turns out that these are the same field. I'll explain to you exactly how, and there's a mapping between the coordinates. Okay, so I wanted to do this in a bit more detail, but let me just tell you the answers, and I'll give you an idea of what goes into the calculation. The way that we make this identification is that we look at how conformal symmetry acts on the bilocal field, and we look at how conformal symmetry acts on the higher spin fields. And we try to find a change of coordinates that takes the generators of conformal symmetry on this field into the generators of conformal symmetry on that field. And it turns out that there's a unique answer to that. So let me be clear on exactly what is the computation that you're doing. So pick up some generator, let's call it Al, and this belongs to the SO23 Lie algebra. And you act with Al on the bilocal. Now, I'm going to call this Al tensor when you act on the bilocal. And the reason for that is the way things act on the bilocal is you've got the sum from A is equal to 1 up to n, and now you do the usual thing. You act on the first scalar field, phi a, x plus, x1 minus, x2, x1, x2 minus, x2. What am I doing? Phi a plus, leave the first field alone and act just on the second. And this Al that's sitting here is nothing fancy. It's the usual action of the conformal group on a scalar field. So, usual SO23 generator on a free scalar. When you want to act on the gravity side, and you see, the reason why I've called this Al tensor acting on sigma is that this is usually how you would act on a tensor product. Act on the first guy, leave the second guy alone, leave the first guy alone, act on the second guy. So that's the usual tensor product action. When we act on the higher spin field, then you see we've got a whole bunch of fields sitting here, and they're each in different representations. They've each got different spins. So when we act on those, what we want to get, we want to get the cos 2s theta. We don't act on that. But now we want the generator for the 2s representation acting on the x plus the sine 2s theta and again the 2s representation acting on that gauge field. So for each different representation that appears in the higher spin gravity, we've got a different conformal generator. And we want to know, is there a change of the CFT coordinates? Not obvious that there is one, but is there a change of the CFT coordinates that takes you from this representation that you know to that one? And let me just unpack what this L to the 2s is. What do you have to do to get L to the 2s? So to get L to S. So the transformation of the gauge field, SO24 is an isometry in your space-time. So for each SO42 generator, you have a killing vector. And you can use that killing vector to generate the transformation of the gauge field. So let me call this delta isometry. So this is the one that you would generate. Let me maybe put killing vector here. That's just what you'd always do when you've got a tensor field and you want to transform it with some symmetry operation generated by killing vector. But in this situation, this is not the right thing to do. And the reason why it's not the right thing to do is you've picked light cone gauge. You've picked A plus is equal to 0. So when you perform some conformal transformation, in general, even though you started with a gauge field that obeyed the gauge condition, after you performed the conformal transformation, you moved out of the gauge. So you have to add to this a compensating gauge transformation that brings you back into the gauge. So you do, let me say, comp for compensating, and this is just a gauge transformation. So you can always supplement a global transformation with a gauge transformation. That doesn't do anything, doesn't change the transformation. And so you would need those two. But you're still not done, because also you need to make sure that when you look at how these fields transform, that you have solved the gauge constraint. And that means, making sure that in that expression over there, anything that you see with a minus index, you replace by its solution to the gauge constraint. So all of this goes into getting this generator L to S. And then the question is, starting from the usual action of SO23 on the scalar field, you use that to get action on the bilocal, is there a change of coordinates that will take you to this representation acting on the higher spin field? And the answer is yes, and let me tell you what that change of coordinates is. So to state that change of coordinates, it is simplest to do the following. So we have the coordinates x plus, x minus, x, z, and theta. What I'm going to do is shifts, translations in x minus are a symmetry. So I'm going to do a Fourier transform on x minus. And if I Fourier transform x minus, so do a Fourier transform, this is just done for convenience so that we can write nice simple formulas. But if we do a Fourier transform on x minus, then we've got x plus, p plus, x, z, and theta. So under Fourier transform, x minus mixes with p plus. This is the variable that's conjugate to x minus. Remember in light cone gauge, the metric is off diagonal, so x minus is conjugate to p plus, and x plus is conjugate to p minus. So this funny minus going into a plus is just a consequence of light cone gauge. In the CFT, we are also going to do a Fourier transform. So inside our bilocal, we had x plus, x1 minus, x1, x2 minus, and x2. We'll also do a Fourier transform. And also on the minus coordinate, and we'll get x plus, p1 plus, x1, p2 plus, x2. So in these coordinates, we can work out this action, that action, and ask can we map them into each other? The answer is yes, and let me tell you what the coordinate transformation is. So x looks like p1 plus x1 plus p2 plus x2 over p1 plus p2 plus. Z is the square root of p1 plus p2 plus over p1 plus p2 plus x1 minus x2. P plus is p1 plus p2 plus theta is 2 inverse tan p2 plus over p1 plus square root, and x plus is related to x plus. So that change of coordinates takes you from the one to the other. And now let me tell you how the fields map, because that's also part of the dictionary. So let's see. Oh, sorry. So let's see. Maybe I can figure this out. Oh. Sorry?
The last one is fixed.
Yeah, the last one is fixed. I want to make this one go up. I thought that was, okay, good. Oh, it only goes to there. I see, okay. So let's see, I want to bring this one down. That's there. Good, okay. So now, what is the mapping between the fields? Sigma of x plus x1 minus x1, x2 minus x2. This has got two pieces. It's got a piece which is the large N expectation value. So this is the large N vacuum expectation value. And then there's a second piece and that's a fluctuation. Now remember, 1 over N is like h bar. So when N is infinity, our field might have a classical piece. That's going to generate the AdS spacetime. But there's a fluctuation, and that's where the quantum fields come from. So this eta gets identified with the higher spin field. And the identification with the higher spin field is the following. Phi of x plus p plus x z theta is equal to 2 pi p plus sine theta times by eta of x plus p plus cos squared theta over 2 x plus z tan theta over 2 p plus sine squared theta over 2 x minus z cot theta over 2. Okay, so sorry I rushed this last little bit, but I wanted to get to the punchline. So what have we got now? Our bilocal field from the CFT has a large N piece and a piece that's a fluctuation. This piece that is the fluctuation, up to some factors of p plus and sine theta, is the higher spin field. And we fixed this now without any input from gravity. All that we've said is we would like the field to transform in the correct way under the conformal transformations, and we want 1 over n to be the loop expansion parameter. What you can do now is you can ask, well, what's the equation of motion for the field phi? Because you know eta. You know eta's equation of motion from the CFT. So now using the CFT, you can ask, what equation of motion does phi obey? And if you go through that exercise, you correctly reproduce the gravity equation of motion for every single gauge field and for the bulk scalar. You get it perfectly. And then, if you go to the boundary of the space-time, if you remember, there was this dictionary that said, if you take the field to the boundary, up to some factor of z, you will get the conformal field theory primary operator. And the conformal field theory primary operator is some complicated expression in terms of derivatives acting on the two fields and some linear combination. If you go to the boundary of the space-time, that's exactly what you get. You get the correct conformal field theory current. So this gives you a set of fields that obey the correct gravity equations of motion together with the correct boundary condition. Now, in AdS-CFT, there were many general theorems that are expected, but you don't really have a simple setting in which you can test it and you can see this theorem working. So one such theorem is called subregion duality, and the question says the following. So I'm going to draw a picture now. This is the x direction, and this here is the z direction. This line here is z is equal to 0. Z is equal to 0 is the boundary of the AdS spacetime. And what you can do is you can study an interval over here. So this is where the CFT lives. And you can say, I'm not going to take the whole CFT. I'll only take the CFT inside this interval over here. So that means when you pick your bilocals, you can put one of the fields here, you can put another one of the fields here, but both of the fields must lie inside that interval of the CFT. So you picked some region of the CFT, and you're saying, this is where I construct all of my bilocal operators. What you can ask yourself is, how much of the bulk can I reconstruct? And by choosing some bilocals, you're going to be able to get the fields in the bulk. And if you've restricted what bilocals you're going to get, you're only going to get a restricted set of fields in the bulk. There's a result known as entanglement wedge reconstruction. And what it says is, you should be able to construct everything up to an extremal surface in the AdS4 space. And this surface is known as the Ryu-Takayanagi surface. And in fact, if you take our formulas and you check what piece of the bulk can you reconstruct, you exactly find you can reconstruct everything inside that surface. So that's actually a very concrete illustration of entanglement wedge reconstruction working. And then the last test that it's passed is, another test that it passed, if you put the CFT to finite temperature, then you expect that you actually have a black hole that's giving you the temperature in the space-time. And whenever you have a black hole, you have some modes where part of the mode is behind the horizon, part of the mode is outside of the horizon, and this leads to these quasi-normal modes that you see for a black hole. From the point of view of the CFT, you would expect some dimensions appearing where the operator dimensions are no longer real. The way to describe this finite temperature field theory is in terms of 2 copies of the field theory, and you use something called the thermofield double. If you've got 2 copies of the field theory, you can construct bilocals where both fields belong to the first copy, both fields belong to the second copy, or one field belongs to the first copy and one to the second copy. So there's a lot more different kinds of bilocals you can define. And you find, in fact, the spectrum of operators in this case does have these quasi-normal modes, and you find them with precisely the right frequency. So it's some evidence that you know something about the horizon, but a lot more is needed to be understood there. And then the final thing that it reproduces correctly is a new result known as the holography of information. And this is actually a property that is expected for any theory of quantum gravity. And what the holography of information says is, if you pick a Cauchy slice in space-time, any Cauchy slice, so let me just draw it like that. So this is any Cauchy slice in space-time. All of the data available on this slice is also available in a tiny neighborhood of infinity. So somehow, if you know what's happening on the boundary of your space-time, a tiny neighborhood of infinity, you know everything that's happening in the middle. So this is a new redundancy that was discovered in gravity. And it turns out that this bilocal holography also has exactly that redundancy. So these last few points that I talked about very much more just quickly. When we have our workshop, is it next week, I guess? I'll be discussing some of these results in more detail there. Yep.
So when you say Cauchy slice, do you mean Cauchy surface?
Yeah, some Cauchy surface in space-time.
But AdS doesn't have a Cauchy surface.
Okay, so good point. If you unfold the time direction, then you have. Yeah. So we actually always unwind time.
Okay.
Yeah. Okay, good. So that was it.
Thank you very much.
Some question?
I have a more general question. So in this setting, which is a very concrete setting, you tested a lot of things said about this AdS5 duality. So you illustrated some of the conjectures, you know how they work and so on. Did you disprove anything? So are there statements made about AdS5 duality which you are able to say in this construction they are invalid?
So, okay, so I wouldn't say that we disproved anything, but I do think that we've clarified certain things. So one thing that I would say that we've clarified, I don't know how the authors of this would feel, is there's this statement that holography works as quantum error correction. And the idea is that the bulk is encoded into the CFT in the same way that you encode messages in a qubits with using some in entanglement, in some quantum error correction scheme. And it was claimed that this is a deep property of gravity. Actually, we would claim that the map between the CFT and the bulk is 1-to-1. This freedom is not there. There's no redundancy. If, however, you decide to put a cutoff and you say this is a low-energy observer and they can only occupy some lowest modes, the act of putting a cutoff introduces some redundancy, and that looks exactly like what the quantum error correction people are claiming to see. So I would say that we've clarified this is not a property of gravity, it's a property of the fact that you put a cutoff into the theory. Yep.
Doesn't the cutoff wreak havoc with gauge variance?
So we put the cutoff in the CFT. Okay, so so this is what you would expect a low energy observer to see in the gravity. Yeah, I don't know exactly how it would be described in the gravity in a gauge invariant way. Yep.
What is your insight on if AdS5 can actually be pushed beyond AdS?
Okay, so I think that up until very recently, there was no evidence that it would hold in space-times that don't have a boundary and things like that. But I would say this discovery of the holography of information changes that. Because the holography of information holds in AdS space, and there you can actually test it, but it also holds in flat space. So this is the first time that we're getting some idea that in flat space, possibly there's a description of the entire space-time in terms of something living at the boundary, and that's not just words, there's actually something to back that up. this still wouldn't help you for something like a cosmology application for de Sitter space or something like that. And even in the flat space case, I mean, there's no precise proposal for how holography would work there. But I would say that's the first hint that maybe holography can apply to flat space gravity.
I have a technical question because you are a bit fast.
Sorry, Dario. Yes.
No, it's,
Yeah.
probably I take the chance.
As the time runs out, I go faster and faster and skip more steps. Yeah.
To give you extra minutes to the question. So, but then you see this Fourier transform. What was the reason you needed to introduce this Fourier transform on one component?
Okay, good. So we first wrote down the map in 2010, and we wrote it down first of all as a classical canonical transformation, and it mixed p's and x's, so it wasn't easy to write it down as just a mapping between coordinates or a mapping just between momenta. So it looked kind of ugly. What we realized, I mean, 8 years later, is that if you do a Fourier transform on the x minus coordinate, x1 minus and x2 minus, then you get this nice, okay, let me try again. You see, this looks like a lovely local, just map between coordinates. That's a property of being in P+. If you still had the x minuses, this would not be local.
So for locality of the transformation.
To have a nice simple map, exactly.
And this, so you apply this L there,
Yeah.
which we know how it acts there.
Yep.
And then you said the subtle part was here. You act with
So you take
to
L
construct this
here.
L2S.
It acts differently on each gauge field component. And to construct it, you actually need the action of the conformal group on this reduced set of degrees of freedom. So you need to do the isometry, add a compensating gauge transformation, solve the gauge constraint, and then solve for the fact that it's symmetric and traceless. And in the end of the day, you get a representation acting only on the two components that you've chosen as physical.
And then you want to compare the results with some identification of phi
So,
with
exactly.
eta.
So that's the identification of phi with eta. So we take these generators acting on the eta, we perform that change of coordinates, and we get that formula. So take the CFT result, make that identification between the CFT field and the higher spin field, perform this change of coordinates everywhere, and the actual CFT generators turn into the higher spin generators.
Lower dimensions, this changes a lot, I guess.
Actually, this is the only case that we know how to do it. Yeah. Yep.
It's probably a dumb question, but so I see those is P1 plus are they restricted to be greater than 0?
Yes, P plus is greater than 0. Yep. So what is P plus? If you write it in terms of energy and momentum, P plus would be the energy plus P1. And that can never be negative.
Sometime after you did this, there was a paper by another group, Aharoni, Chester,
Yes.
Thompson. They have a different way of mapping
Okay.
from CFT to it. Yes. The
So
same theory,
what they are
but-
doing is they are taking the product of the two scalar fields. They're then using a Clebsch-Gordon coefficient to extract the spin S component. So it's exactly the same logic. You're performing a change of variables, but they are just systematically introducing Clebsch-Gordon coefficients everywhere. That means that they can easily write down formulas for other CFTs and other dimensions, but they're in some sense formal expressions, because to actually evaluate the Clebsch times the two scalar fields, you have to do some integrals, and those you can't do analytically.
So does it reduce to your mapping in
Uh,
3D? Or?
So, for example, they do block expansions, conformal block expansions of certain correlation functions, and they match exactly the block expansions that we have with the same OPE coefficients. So the two look identical, yeah. Yep.
Is there any way to like get odd spins out of the CFD?
Yes. So in the Vasiliev theory, there is a version that has all spins, also odd. And then the CFT that you would consider is the CFT with a complex scalar field. And soon after our paper appeared, Polchinski worked out that case with a complex field.
So what happens if I try to put fermions? Can I try to put a free fermion?
So much less has been studied. So a map has never been worked out in that case. Strominger studied that case of free fermions first, and he claimed that the dual to that would be de Sitter.
De Sitter.
Yeah. So I don't know what the status of that is. I didn't keep up with it. Yeah.
Was the real proper fermions with spin 1/2, or was the Grassmann?
No, proper fermions at spin 1/2. Yep.
Because I thought that was coming from these symplectic fermions like that you send n to minus n essentially. Is that you have just scalars which are actually Grassmann scalars.
Oh, maybe. Yeah. I don't know. I didn't see that version. It would be very easy to work this out for fermions, and